A&Maya Tech Department, Room 7. What may seem to be a calm and peaceful room is actually a wild jungle, and every jungle must have its king. The king of this one is this magnificent beast. Powered by 4-wheel drive, topping out at a max speed of nearly 1 meter per second. This robot is a ruthless fighting machine with a long track record of success. Dominating every competition it's been in, it has garnered a respectable win rate of 13 wins, 6 losses, losing only to unforeseen circumstances. I have the pleasure of showing some never-before-seen footage of this magnificent creature in action. Watch as it smoothly grabs the cube and lifts it into the air. The robot now begins to move. It seems to have turned the wrong way though. Oh my, it has dropped the cube. But the robot is determined. It now engages in physical combat with the cube. What will it do now? Backs up, opens the claws. Seems to be agitated cube. Now it goes in for the kill. Latches up viciously. Slowly drags it across the playing field. Lifts it high into the air. And slowly, as if it is tormenting the cube, drops it over the fence. What a beautiful display of nature. It seems a competitor has now appeared. But let's see how the robot deals with this newfound opponent. This opponent seems to know what they're doing. What will the king do next? The king extends its lift and its claws to show dominance over its opponent. It then drives towards the fence to block the opponent from getting its studs over. Let us see if the king is successful. And what a beautiful block done by the king. How did such a perfect robot come into existence? To answer that question, we must go back to the very beginning and watch the evolution of this robot. This robot was created for the VEX Robotics competition, Starstruck. In this competition, two two-man teams, one red and one blue, tried to throw stars and cubes over a fence so that they can gain points and win the match. Now, 1 star is worth 1 point in the near zone, 2 points in the far zone. A cube is worth 2 points in the near zone and 4 points in the far zone. A robot can also try and hang 4 points if it's below the black bar, and 12 points if it's above the black bar. This will be the second time I've competed in the VEX Robotics competition. Last year, I competed in the VEX Nothing But Net competition. My team and I performed extremely well in it, and even advanced to the Create US Nationals located in Council Bluffs, Iowa. At this tournament, we competed against 200 of the top robotics teams across the US, and achieved a respectable win rate of 5 wins to 5 losses. But unfortunately, we were eliminated in the first games of the playoff. My goal this year is to return to this competition and outperform the results that we achieved last year, using the knowledge and experience we gained from those events. The first step to building this robot is of course design and research. I'm going to need to research the specific game rules for the VEX Starstruck competition to see if there's anything important I need to know, and I need to design potential robot concepts and figure out which one would be most effective for this competition. This stage is easily the most important stage of this process. Without this, I would even have a robot. Of how it's gonna work. The fence is around 31 inches tall, so we need something that can reach the height and knock the stars over. What we have down here is a basic kind of laundry system. We're thinking about a dumper that the claw or the bucket, the thing that grabs the stars, will deploy out like that. And it looks something like this. So there'll be a fork on the bottom with 2 pieces that can move around, like move out and in. So this way it's like a fork that goes in underneath the stars, and then what it will do is that it will grab them, and then grab it, and then you can lift it and dump it across the fence. And over here I was thinking of potential drive systems that will go. These were the 2 big main popular ones I saw online that could work. This is the standard sort of 4-motor drive, very basic, very easy to build. And then over here is something called an X-Drive. It's different, and it's got
the ability to strafe, so it can go side to side. While this one you'd have to turn to go from side to side. So this one can strafe, but the only issue with it is that it's got a low speed compared to this, because this, every time it moves somewhere, it can only move diagonally-ish, and it wastes energy when it does. So I'm probably going to continue these, and then in the end I'm going to choose one and model it in Inventor, and let's catch up then.
Okay guys, so I'm in Autodesk Inventor here, and I'm just going to be making some of those drawings I was designing the other day into 3D models that I can use for reference. I've started working on over here the robot chassis. Let's load that up. So basically what Autodesk Inventor is this 3D modeling program where you can model designs and all that, so it's easier to do. Like, for example, we have this is the robot chassis. This is the drive system which we want to be using for a robot. I have it modeled all here in Inventor, as you see that over on this side. It's really useful because it shows you all the parts you need, and you can highlight them and see, and you can also measure the distance between some of these parts. Say, for example, here and here, that's 1 inch. So you're like, oh, okay, 1 inch. You need at least a screw that's 1 inch long to put in there. So, oh no, okay. Pokemon just stopped responding for a second. Well, so that's that. I'm going to be continuing to work with Inventor, obviously, and then my next aim is going to be making the claw and lift mechanism for the robot in this program. After the design phase is over, it's time to actually build the robot. In this phase, I will be taking the designs that I made and I'll make them into actual working robots, and I'll be prototyping and testing to see if these designs live up to the theoretical standards. And if they don't, we'll just have to revise and potentially rebuild. After the robot is completely built, the next step in the process is coding. I need to program the robot so that I will be able to control it with a controller, and it also needs to be able to drive autonomously for a 15-second autonomous period that happens at the beginning of each match. Okay, nice. So what I wanted to do today was work on the autonomous program, and since I have outlined a few designs already, if we keep going down over here, we'll find the autonomous task. So this is what happens during the autonomous task. It's in a loop known as a while loop, so it will constantly be running, and this will continue running until the 15 seconds is over. So what it does first is it gets the sensor values for the sensors I put at. As you know, I have the potentiometer on the claw and the potentiometer on the lift. Now these two potentiometers, they give you the value of the position that the axle is, and we can use that to figure out what position the claw is, whether it's closed, open, or what position the lift is in, whether it's up, down, or what in between. And then these two are known as shaft encoders. These are those red boxes that were attached to the drive system, and what they do is they basically allow the robot to it allows the robot to count how many times the wheels have turned, and we can use that to figure out how long we need to turn and track it. And then if we want to turn a certain amount, we track this value, and once it reaches that value, we can stop it. And with that, the robot is done and ready for competition. Thanks folks for following me on this journey to find the origin of the perfect robot.